So we're on 2A.4, and we're starting off our exponential, diving more into exponentials. Yeah, you can. Yesterday, we kind of briefly went through our properties of exponents that you need to recall from Algebra 1 and Algebra 2. So going over our properties, just remembering our distribution property, the two types of distribution properties, remembering our product property, so product, remembering our rational property, our rational exponent property, our negative exponent property, and when you are dividing with distribution, okay, and how they apply. Then we talked about when there are values other than 2, 3, integers, values other than integers, more than likely that's an example of needing to be able to put it into the calculator. And I gave you all time to practice inputting into the calculator. Are there any questions on practicing and inputting into the calculator? We're good? All right. So we're going to go on to characteristics of exponential functions. So these are the overall characteristics of exponential functions that we need to make sure we're comfortable with and can recall these properties, okay? So to begin with, this is our standard form. Our parent function form is b to the x. That's when your a is 1. And the range, so your domain is all real numbers. Our domain is from negative infinity to positive infinity. Our range is all positive numbers. That's because it's from 0 to infinity. Okay, your parent function, b to the x, that means no transformation, no nothing. The intercept that it's going to have is going to always be 0 to the 0, 1. And that's because anything to the 0 power is 1. Makes sense? So parent function is going to be y-intercept of 1. Okay? Now, if b is greater than 1, so if our base is greater than 1, that is an increasing, and we're going to say, and it's concaved up. Okay? If b is between 0 and 1, that is a decreasing, but it is still concaved up. Okay? It never crosses the x-axis because there is a horizontal asymptote at y equals 0. And this is a one-to-one function, and it's one-to-one because it passes the horizontal line test and the vertical line test when you're looking at it visually. Algebraically, what you're saying is that for every x value, there's only one y value, and for every y value, there's only one x value. There's no shared outputs.
For 4, is that like, what's that doing?
It's a decreasing from left to right.
It's still going up?
It's decreasing from left to right. Your x's are increasing, but your y's are decreasing, which makes it a decreasing function. It's still concaved up, like the shape is still a concaved up situation. I'm not concaved down.
Oh.
Okay. All right. So you got this. Everyone has moments. We need a break. All right. So these are two examples that we're going to graph. We're going to graph an example of an increase and an example of a decrease. How do I know which is which? Exactly. So the increase is when my b is greater than 1. So my increase function is going to be f of x equals 2 to the x. My decrease is when when b is less than 1 but greater than 0. So my decrease is g of x equals 1/2 to the x. You cannot have a b that's less than 0. No negative b's allowed. It's undefined.
Like
you'll get error.
Alternate. Like you can see it kind of like you can see the line on the graph it's like a really big negative number and then a really big positive number. Right? Yeah.
All right. So now we have to graph it. So key thing is when you're graphing both, we said that when you're in standard parent function function, that means your a equals 1. So you're always going to be, for both functions, their y-intercept is at 1. We also are going to have a horizontal asymptote at y equals 0. Okay, I'm going to graph our f of x first. Put it in parentheses and then put the power. Oh, it's gone. It disappeared. Yeah. All right. All right. So here we go. I'm going to just plug in values really quick. So 2 to the 1 power is 2. 2 to the 2 power is 4. 2 to the 3 power is 8. 2 to the 4th power is 16, right? And then it would be 2 to the -1 would be 1/2, and it keeps going, right? So this is what I'm concentrating really hard, guys. I'm going to hit every single point. Bam. There we go. All right. So now we're going to do our 1/2 x. So this is going the other way. Again, it starts at 0, 1, each one. But now, when you're thinking about a half to the x, you're looking at the opposite of it, what's taking place. So 1/2 to the 1 power is going to be 1/2, right? 1/2 to the power of 2 is going to be 1/4. So it's getting smaller and smaller. Okay. 1/2 to the -1 means I'm doing what with this 1/2? It means I'm reciprocating it. I'm flipping it. So it becomes 2 over 1. So 1/2 to the -1 is 2. Because it's 1 to the 2 -1. And if it's in its wrong location, so.
So the -1 on it.
Well, this is also -1, which is why it flips along with it.
Okay.
Yes. Okay, so with that same knowledge, if I have 1/2 to the -2, what ends up happening?
It's 2, right?
It becomes 4 over 1. That's because, again, 1 to the -2 over 2 to the -2 tells me that they both are in the wrong place. Okay, it's the opposite, not the inverse. Okay. All right. So then, if I'm at 3 now, now that we see the pattern, what would be 1/2 to the -3? 8. 1/2 to the -4. 16. So now I'm doing this, which is why it's a. That one didn't go so smooth. I tried. We're gonna do it again. I'm not a quitter. Here we go. I can go through. Oh, I'm gonna go through all these points to the best of my ability. Okay, pretend that that's like the best you've ever seen. It's gorgeous. I know. Okay, so when we look at this, what this is describing is that there's a relationship here, right? And that relationship is that when I have 1/2 to the x, it is the opposite of this, which is 2 to the -x. And that makes sense because in transformation world, when my x is negative, what does it cause it to do? Yes, your signs. In transformation worlds, when your x is negative, what does it cause your function to do? Reflect over the y-axis. When your x is negative, that means it's a reflection over the y-axis. And because 1/2 to the x can be rewritten as 2 to the -x, that is why that reflection happens. Okay, so this leads us to our transformation rules. So just like before, if I have a vertical translation, my vertical translation is adding or subtracting to my y, right? F of x means y. So to the whole function, I'm adding or subtracting. So when I have 2 to the x plus 4, I'm saying I'm shuffling, translating that 4 units up. If I have 2 to the x minus 5, I'm translating 5 units down. Horizontal translations is where we like to remember our x's are what? Okay, so the rule is f of x minus h. So if I have 2 to the x minus 3, it's going to cause the function to shift to the right 3 units. If I have 2 to the x plus 6, it's going to cause the function to shift to the left 6 units. Okay, vertical dilation. And we say dilation because that's our stretch or our compress, right? We're stretching or compressing. And so we call it a dilation. We're now in pre-cal, so it's a dilation. All right. Your A is your coefficient in the front. So looking at your A, it's the absolute value of the A on whether it's a stretch or a shrink. So here it's 3. And because it's greater than 1, then therefore it's a stretch. Here I have a half. It's less than 1, but greater than 0. It's going to be a shrink, a compression. Yes?
So vertical, anything if it's a coefficient or like, yeah.
Yes.
And then horizontal, it's
the coefficient of the x only.
Yeah.
Yes. Yes. Okay. So your horizontal dilation, it's opposite. It looks like multiplication, but it's actually division. Okay. You're actually dividing by that factor. And so it's the opposite of what you think. If I'm between 0 and 1, it's going to be a stretch, a horizontal stretch. If I'm greater than 1, it's going to be a horizontal shrink. Okay. So X is always the liar. X is always doing the opposite of what you think. Okay. Then our reflections. If my negative is on the outside, only affecting my coefficient. So if my leading coefficient is negative, then it's going to be across the x-axis. If the x is on my negative, if the negative's on my x, then it's going to be across the y-axis, which is why when we have 1/2 to the x, because it can be written as 2 to the negative x, notice that it's a reflection across the y-axis of 2 to the x. Okay. All right, so these are your specific transformation rules for exponential. These are our general transformation rules for all functions. These are the ones specific for that one. These are the general. Questions about either? All right, so we're going to go through and write in how they affect. So your vertical translation means that you are adding or subtracting to your y. Yes? Your horizontal translation means you are adding or subtracting to your, to your x. Your vertical dilation means that you are multiplying, right? So it's your A times your y. Your horizontal dilation means that you're dividing. So it's your x divided by, is it okay if I change this to B? I hate that the writer of these notes made it A twice. It bothers me. Okay. And then this depends on whether it's reflecting over the X or the Y. Either way, they affect either one. So this is affecting the Y, this is affecting the X. Okay. The transformations are all based off of the parent function of that base. So we're going to go through and do an example with 3 to the X.
Or just say the by a factor of. Is there a paper that's different? Or is it by a factor of absolute value of A and by a factor of 1 over A?
Oh, that's just write it in. Like write what I wrote in the blue. That's what that means. By a factor means you're multiplying by A. So just write A times Y. Like where it says vertical dilation, just write A times Y. That's what this means. This is this. This is that. It doesn't say dilation. It's called a dilation. You can write stretch and shrink. It doesn't really matter as long as you know that's all a dilation. It's a vocabulary difference. All right. Yes, are we ready to apply our knowledge? Can I go? All right. So we're going to, y'all have 3 to the x, right? All right. We're going to be modeling this with 3 to the x parent function. So the first thing we're going to do is fill in the parent function values, okay? And then we're going to apply those changes to those values. Got it? So starting off here, we have 3 to the x, and we're going to fill in what it would be. So what is 3 to the negative 2? 1/9. 3 to the negative 1. When you have a negative power, that means that it belongs in the denominator. So yes, 3 squared is 9. Okay. Can you answer, please? 3 to the negative 1 is 1/3. 3 to the 0 is? Okay. And then 3 to the 1 equals 3, and 3 squared equals 9. So this is our parent function for 3 to the x. Everything else from here is a transformation of it. So looking at what's given to us, our g of x is going to be 3 to the x plus 2. Without completing it, what are we doing to the parent function? Which way are we going? X's are liars, so we're going to go left 2. If I'm going left 2, who is being affected? Just my x. Am I touching my y's? No, my y's are not being affected, only my x's. Does that make sense? Yeah? So then what are my new points for g to the x? We're going to write them as ordered pairs. There we go. So I'm changing each x, right? So to each x, I am subtracting 2, correct? So I'm going to write it out fully first, and then only for the first one, and then I'll stop writing it from there. So I have negative 2 minus 2, comma, 1 to the 9. Does that make sense? Oh, sorry. That's what I need to keep teaching. Does that make sense? I'm moving the x's. No, maybe. We're doing it in the using the transformation. Yes. Oh. Yes. Look at your posture. This is gonna be like so they let me do it last year. We just went and bought it. Okay. Here we go. So the purpose of knowing your transformation rules is to try to help make the process just a little bit faster. And so you have to multiply multiple things or add multiple things. Is just saying, what am I doing to the parent function? And if I'm shuffling it to the left, that means I'm adding or subtracting, subtracting from the x that I currently know, right? So then this is just going to be at negative 4, comma 1/9. This is going to shuffle. So I'm now doing negative 1 minus 2 is going to put this at negative 3 1/3. What's going to happen here? I'm going to be at negative 2, comma 1. I'm going to be at 1, negative 1, right? Comma 3, and then I'm going to be at 0, comma 9. Okay? Your y values stay the same because the only effect that you have here is on the x, right? And so you're literally just taking your parent function and shuffling it. So my parent function, when I graph it, if I was to graph it, again, it always starts here. 3 was at 27, which I can't get to. Did not mean to put 3. 1 was at 3. 1 was at 3. 2 was at the very top. So we're gonna say it's like this. So when you just plug the x values into the new equation, you can. It's just that it wouldn't be on this, like it would be values that aren't necessarily there. Or you would have had the -2 and keep going. But yeah. But the purpose of transformation rules is that you're not plugging in, that you're just shuffling. Okay? Yeah, go for it. Me probably getting in trouble again. so -4 and 1 9. So we're just shuffling everything. So now -2, 1, -1's at 3, and you know, it's beautiful. You see that? Thank you guys. I do what I can. Okay. It's beautiful. Okay. When you're making horizontal and horizontal translations, is that going to change your domain? No, because our domain is regardless still what? Negative infinity to positive infinity. And our asymptote, is it going to change with horizontal? No, our asymptote. So we're still at 0 to infinity. Okay. The only thing that's going to change that is if I make a change to the y. And did I change the y? No, our y value stayed the same. Okay. The domain is going to stay the same because it's infinite, right? But if I changed my up and down, that's going to affect my intercept, my asymptote. I'm sorry. All right. So now when we're looking here, we're going to talk about how can I rewrite this. So on part 4, we're talking about, okay, if I have 3 to the x plus 2, could I rewrite that as a exponential function in the form of a times b to the x? And the answer is yes. Okay. So currently we just graphed our g of x, and our g of x equals 3 to the x plus 2. Okay. Our g of x can be split. If I'm adding 2, remember the rule is if you are adding 2 exponents, that meant that they came from multiplying 2 numbers with the same base. Do you remember that exponential rule? Let's go back and look at it. If I am adding 2 of them, that means that they came from numbers with the same base, right? If I'm adding the exponents, they came from numbers with the same base. So I can split this. This can become 3 to the x times 3 to the 2. So when I ask me, can I rewrite this as a h of x in the form of a times b to the x? Is that possible? Yeah. Yes, because 3 to the 2 is my a, and what is 3 squared? 9. And then I still have 3 to the x. So this is the exponential of that function. Okay, without transformation. So this is just 9 times 3 to the x, and that's using our exponential rules. All right. Okay, did we finish part 1? Yeah.